Whoops. This this presentation is the result of um, of an astronomical discovery that occurred about 6 months ago. It has to do with a dwarf planet, one that you may have or may never have heard about, called Quaoar. Quaoar is a trans-Neptunian object. It's in the Kuiper belt. Um, what they discovered was that it had a ring. And about a month later, lo and behold, they found out it has two rings. Well, that by itself was not the big discovery. What happened was they figured out where those rings were located relative to Quaoar, and they were really surprised to find out where it was. And it's now a mystery, but the solution to that mystery may lead to a better understanding of the solar system and how the planets formed. So I think that this could lead on to something more important than just finding out that a dwarf planet has rings. So let's go and start with rings here. A ring is a disk composed of solid materials such as ice and dust particles. Within a ring system, the rings can be either dense, made of fairly large particles, or they can be, the ring could be dusty and pretty flimsy. Rings are rapidly evolving structures due to gravity, viscosity, and radiative forces. The known ring systems are all very different, which makes it very difficult to come up with a single theory to explain the ring structures. In fact, as I was telling Ron earlier, there really is no single theory that will explain the rings. A lot of rings are made one way, but other rings are made a different way. We know that for a fact. So there are different mechanisms that can lead to the same type of formation of rings. Let's see. Yeah. So let's go on over here. And, oh, okay. Yeah, why not? Time is a charm. I hope that continues to be the case. So what I want to do here is to show you different objects within the solar system that are known to have rings. We're going to start off with the sun. Usually when you go into astronomy books and things of that type and they talk about rings, they never talk about the sun having rings. Thing of it is the sun actually does have rings. It has dust rings. It has 3 dust rings. They're co-orbiting with the inner planets, Mercury, Venus, and Earth. The main asteroid belt is a ring around the sun. It contains hundreds of thousands of objects called asteroids. And then we also have a second asteroid belt called the Kuiper belt, which is basically beyond the orbit of Neptune, and it contains a lot of different objects as well. Then we have the gas giants, Jupiter, Saturn, and Uranus, and Neptune. They all have rings. In addition to that, we have dwarf planets that have rings. We got Haumea, which is a Kuiper belt object. It has 1 ring. And as I mentioned, Quaoar, Quaoar, it has 2 rings that we know about now. And then the minor planets and comets even have rings. Case in point is Chariklo. Chariklo is a Centaur object, and it is known to have 2 rings. There's Chiron, 2060. Now, the thing about Chiron is is very interesting. Chiron has two different astronomical designations. It's called 2060 Chiron, which it designates it as an asteroid. It also has a 95P Chiron designation, which designates it as a comet. Thing of it is, it has characteristics of both. Nobody knows how to categorize it, so they gave it two different astronomical designations. Now, Chiron, they think, they're pretty sure that Chiron has rings. They have studied it. They have not confirmed that it has rings, but as far as we know, it's very likely that it does. And in addition to that, looking at the moons of the planets, there are two moons of Saturn that are embedded in rings, which is kind of different. These rings are not around the moons are inside the rings, which makes it kind of interesting. I got four different theories for the formation of the rings. As I mentioned, these are really not theories. I have misnomered this chart. This is my own categorization of different mechanisms that can be involved in ring formation. So the first one here is that the matter in the rings is actually the stuff of which moons are made of. The primary body that was formed creates a gravitational field around it that then puts what is called the Roche limit, so that for anything within that Roche limit prevents the formation of a moon. So instead of the formation of a moon, you're left with a ring. The second theory here is that the matter in the rings originated from a secondary celestial body. The secondary body wandered inside the Roche limit of the primary and was ripped apart by the tidal forces that constitute what the Roche limit is all about. The third theory is that the matter in the rings came from the primary body itself, and primarily being matter that has been spewed out from the internal structure of that body to create the matter in which the ring was formed. And then the last one here is the matter in the rings is material from an asteroid or comet impact, where you have something of that type impacting another body, spewing out material, and that material then forms a ring around the body that was impacted. Now, if you notice, I'm sure, two of these so-called theories involve what I call the Roche, well, it's called the Roche limit. So what is the Roche limit? The Roche limit is on the next chart here. Okay, this is a picture of the man that the Roche limit was named after. What's his first name? I can't remember his first name, but anyway, this is a picture of him. He lived in the 19th century. I think that he came up with the formulation for the Roche limit right around about 1867, which indicates that he did he is very good at mathematics, because to come up with that formulation takes a lot of mathematical knowledge. It's not an easy derivation. I'm sorry, he actually did it in 1848. I got him mixed up with Kirkwood. I'm sorry. But anyway, 1848 is when he did this. But so what is the Roche limit? The Roche limit is the distance from a celestial body within which a second celestial body, held together only by its own gravitational force, will will disintegrate because the first body's tidal forces exceed the second body's self-gravitation. So if you look at at the definition, you basically have now two bodies. You have what you might call a primary body that has a gravitational field. And you have a secondary body that is nearby, so that when it comes close to that first body, that limit tells you when the tidal forces produced by the first body on the second exceed the gravitational force inside the second body. What happens then is that secondary body then is pulled apart and it disintegrates. Okay, so going into that a little bit more. Whoops, what happened here? Oh, I'm going the wrong way. Gotta go the right way. So does anybody know what the tidal force is? Can anybody explain what tidal force is all about? I don't see any hands. I don't see anybody on the online. Ah, you got something, Gary. But if you can't come up with a mathematical formulation, that's okay. A lot of people can't, and I couldn't either if I was pressed to do that, if I had tried to do that like 6 months ago. But I came up with a neat method that you can use to not only come up with a mathematical formulation, but also do a great explanation of what the tidal force is all about. And it's right here. Think of a body and internal to it, pick a point, pick a material point within a body, and you have then a second body that produces a gravitational attraction on that point. That gravitational attraction on that point within the body can be looked upon as having two components. The one component being the acceleration of gravity on the center of mass of that body, plus an increment due to the tidal force. Okay? That gravitational attraction on the center of mass in the body is nothing other than my good buddy's theory of gravitation man, Sir Isaac Newton, saying it's an inverse square relationship between the force on the body and the mass of the body. Okay, so it's a simple formula. The gravitational attraction on that center point is a constant, but the increment that you have on that point that you picked, which is what I call the tidal force, is a variable. It depends on what point you picked within that body. Okay, so we know what that gravitational force is on the center of mass. So what's the tidal force that remains? Well, the tidal force is nothing more than the difference between the gravitational attraction of the center of mass and the gravitational attraction on that point. So you take the vector, you can compute that force on that point by using Newton's law, and you subtract from that the force on the center of mass, and you can come up with the force from the tidal component. So showing you a little bit more on the next chart. Whoops. On the top, I show the gravitational forces on a body. So I have two bodies here, the one that's starting in blue and the other one that's in white. The gravitational force on any one of those points is nothing more than a force that obeys Newton's law of gravitation aligned with the vector from that point to the center mass of the attracting body. Okay, so that's an easy thing to do. But if you notice, each one of the points in this body has a different vector. Those vectors point in a different direction, and they all are of a different magnitude. If you go and look at the second illustration on the bottom, what this shows is what remains when you subtract the force, the gravitational force on the center of mass of that body that you're talking about. Those remaining forces are the tidal forces. But look where they're pointing. Those tidal forces are pointing in different directions depending on the point that you're looking at. So let's go to the next slide, and this is what you wind up with. All these forces, just like Gary told you, the forces from the tidal effect both squeeze the body and stretch it at the same time. So they're stretching along the axis, between the two bodies, but they're squeezing in the direction transverse to it. And that tells you what happens in the case of the, two bodies next to each other, with one body producing a tidal force on the other. Obviously, the same thing happens on the other body. The thing of it is what's interesting about this is if you look over what happens over here at point B, this is the tidal force vectors over here on this side, but look what direction they're pointing. This is a gravitational effect from a gravitational theory. But even though it's a gravitational effect, those vectors are pointing opposite to the body that's producing that. This is anti-gravity. So what happens is that if you're on an asteroid, you're an asteroid you're an astronaut out there in the solar system, and you're doing a survey of an asteroid, and you're walking along on it, and you start to see these particles levitate off the ground, you do something. What you do is you get out your communicator and you say, Scotty, beam me up, because that asteroid is going to disintegrate. So this is an illustration that shows that. You can see that when a body gets within the Roche limit, that it actually is being stretched apart and squeezed at the same time, causing that body to disintegrate. And what happens then is after that disintegration, those particles still exist, but instead of forming one body, they now form a ring around that planet. So this is a good illustration of what happens in that case. Now, this actually was observed to happen back in 1994. Actually, I think that the first observation, this is the comet Shoemaker-Levy. I think it's Shoemaker-Levy 9. Is that the name of it? Yeah, Shoemaker-Levy 9. Back in 1973, Levy and Shoemaker both made an observation of a comet that was not in orbit around the sun. It was in orbit around Jupiter. It was the first and only comet that has ever been discovered that was not in orbit around the sun, but was in fact in orbit around a planet. And if you count all the different parts, and in fact, this is not a single comet anymore. When they first discovered it, it's now 21 different particles. What's interesting about this one here is that what they did was they used a computer to propagate the orbit backwards. They found out that this comet had made a close encounter with Jupiter about 1 or 2 years earlier, and it got so close it was within the Roche limit of that comet, and the tidal force is broken apart into 21 parts. What's really neat about this is that after this picture was taken here, those parts of the comet, the 21 parts of the comet, hit Jupiter. And they hit Jupiter on July the 16th to July the 22nd. What's important about that date is that that was exactly 25 years after the first man landing on the moon. So Mother Nature, using the Roche limit, produced a 21-gun salute to Apollo 11 for its 25th anniversary. So there's not a single formulation for the Roche limit. What I think his name was Edward Roche did was he took the hard thing. It's more or less easy to come up with a formulation for the Roche limit if you make an assumption that it's a rigid body, even though it's being deformed. You can come up with an estimate for the Roche limit using that. What he did was he assumed that the surface of the body was actually being deformed in an ellipsoid, and he came up with a better estimate for what the limit might be for the tidal forces to overcome the gravitational forces. And he came up with this formula down here. It says the Roche radius is equal to some constant times the planetary radius times the ratio of the densities of the planet and the satellite to the 1/3 power. So it's an inverse cubic relationship for the densities of the two bodies involved. His actual formulations had for the constant 2.456. As you can see, the formulations for the other assumptions are of the same form, just with a different value for the constant. So the constant ranges from about 1.26 to something like about 2.45. So when you read something in the astronomy books, if they don't say otherwise, they just talk about the Roche limit, you should assume that they're talking about the constant 2.456 in the equation. So since we're dealing with the ratio of densities, what I'm showing here is the estimated densities of known asteroids. And the vertical scale on here is mass, which is an exponential or logarithmic scale. And on the horizontal scale, we have the distance from the sun. This area over in the left-hand side that I have colored in is my estimate for those asteroids that may be applicable to the Roche limit. One of the important things about the Roche limit is it's not applicable to all bodies. When it comes to asteroids, they're applicable to basically what I call rubble piles. And I'll show you what I mean by rubble piles in just a minute. But the rubble piles are basically nothing more than a bunch of rocks that are, have come together to form one body. But there's no internal tension forces that prevent those particles from actually leaving. The only thing that's keeping those particles in is the mutual attraction, gravitational attraction between them. So this is what I call rubble piles right here. These are actual pictures of asteroids that have been visited by different spacecraft. One thing, if you look in the upper left-hand corner, that's a very interesting picture. What you're looking at, what appears to be one asteroid is actually two. There are two different asteroids that have come together and formed a single body. We know that because of the scientific data that has been taken of that particular body. It turns out that the left-hand side has a density of 1.75 grams per cubic meter, but the density of the right-hand side is 2.85 grams per meter or cubic centimeter. So we know that those are two asteroids that have fused together, but they're both basically rubble piles. We know that they're rubble piles because of the low density. You get densities right around about 1 to 2 grams per cubic meter or centimeter. You're talking about bodies that are very lightly dense. The Earth's density is somewhere about 5.5, 5.6 grams per cubic centimeter. And it gives you an idea that when you're talking about something on the order of about 1 to 2, you're talking about something that's pretty light. Same thing with the other asteroids that's shown over here. One thing that one thing I'll point out here is look at the asteroid in the lower right-hand corner. That asteroid is the asteroid Bennu. It was explored by OSIRIS-REx. OSIRIS-REx, if you might remember, has been in the news recently. In fact, just last Sunday, the OSIRIS-REx capsule landed in Utah, and inside the capsule it had about, I think it was 2.5 kilograms. Well, it's about 2 kilograms, I think, of the asteroid Bennu. So that capsule has been recovered, and they're doing analyses of the material right now as we speak, and I expect that we'll find out some interesting things about what they've discovered in the news fairly soon. And for Richard's sake, wake up, Richard. We have something interesting here. It's a stamp that was issued by the United States Postal Service. It was issued on September the 22nd, which was 1 week ago today, but it was 2 days before the capsule landed in Utah. So you talk about an optimistic situation here. They were pretty confident that they were actually going to get OSIRIS-REx capsule back intact so that this would be a fitting memorial for that mission. But they were really counting their chickens, I think, ahead of the time that they hatched at the time. So I thought that was kind of interesting. One thing I did here was I was thinking, we got a lot of moons in the solar system, and I was wondering, are any of those in jeopardy right now of being disrupted by tidal forces? So what I did was I came up with the Roche limit for 2 extreme cases. One for for the fluid case, where you have an assumption that the body will the body actually changes shape. And I have another one for the rigid body case where the body stays the same. So based on my calculations, I have come up with these numbers that I show on the table here. And all the negative numbers, which are shown in red, are indicative of those bodies, those moons that are inside the Roche limit for that particular set of assumptions, rigid or fluid. And as you'll notice, a lot of moons right now are inside the Roche limit, at least for the fluid case. Keep in mind that the Roche limit is good only for the case where the bodies are rubble piles, and also keep in mind that one of the primary assumptions is that in both cases, the internal forces that are active are nothing more than the the gravitational force that is keeping everything together. It doesn't account for any tension forces or anything of that type. So even though they may be shown as being inside the Roche limit, they still have a lot of time left before they actually get into a, a, a location near the planet that's near enough where the tidal forces may exceed the gravitational forces. But I think it's kind of interesting here, at least according to my calculations, it looks like the moon that's in most dire circumstances is Neptune's moon Naiad. And in fact, if you look at this, not only is it well within the Roche limit for the fluid, I'm sorry, for the fluid case, it's also very close to being near the Roche limit for the rigid case. So if you're thinking about maybe building a home on a moon in the solar system, I would recommend not looking at Naiad. Okay. There's a couple other ones here also. We have two moons of Jupiter that are pretty much in the same situation. One thing that I found a little bit interesting about this is that the moon in the solar system that is nearest to its planet is Phobos, one of the two moons of Mars, and Phobos did not show as being quite as bad off as the other moons that I mentioned. But there's something interesting here. This is a picture of Phobos that was taken years ago by one of the spacecraft. And if you notice in the picture, there's a big crater near the top of the picture. I think that's the crater Herschel, named after the astronomer Herschel. And it was initially thought that those striations that you see around that crater were caused by the stresses when that crater was formed by an impact of another asteroid. However, most scientists have now changed their minds and they think that instead of stresses built up by the crater, the stress is built up by the internal tidal forces within Phobos. And Phobos, they think, may be torn about or torn by the tidal forces sometime in about 30 to 50 million years from now. So here again, if you're looking for building a home out in space, you're probably good for about another 30 or 50 million years going to Phobos. Okay, thought I'd throw this in here. Talking about Phobos, we actually have a spacecraft that has not been launched yet. It's a spacecraft that the Japanese have built, JAXA. It's going to be launched next year, about a year from now, September 2024, and it is heading to Phobos, and it's actually going to land. And it'd be interesting to see what instrumentation they have on there and what data it brings back. It may give us a better idea of what is causing those striations on Phobos. I have shown this chart here too. What this chart is it has shrunk all the planets down so that they have been synchronized, I guess you could say, where each planetary radius is the same. So, for example, and this is for the giant planets here. We got Jupiter, Saturn, Uranus, and Neptune with a common radius here. So every one of those planets has been shrunk down so that the radius of each planet looks to be the same size. And what this shows you is the location for each of those planets of some of the moons, and more importantly, where their rings are located. most of the rings, as you can see in what I've shown here, color coded, is all the color coding is within the Roche limit for each of those planets. What you can see here is that in the case of Jupiter up here on the top, there's a little bit of a ring that's outside the Roche limit, which is not what you would expect. However, that's explainable because that's called a Gossamer ring. It's very thin, but they're pretty sure it's composed of material from two moons, Amalthea and Thebe. Those two moons, they think, have volcanic activity and spewing out material that is feeding that Gossamer ring. Same thing on Saturn. Most of the rings that you see around Saturn are within the Roche limit, but there are some that are not, especially the E ring. The E ring, again, is thought to be produced by several of the moons, in particular Aegean and Enceladus, and those moons are believed to be erupting, also spewing out material that's feeding those rings. Like I said, there are different mechanisms that can explain the formation of rings. So the rings that we see in a telescope are one type of ring, but the rings that are outside of the Roche limit seem to be very tenuous, sort of gassy material, and are probably formed not by disruption inside of a Roche limit, but instead formed by expulsions from volcanic activity on some of the moons of that planet. Same thing for Uranus and Neptune. Actually, Neptune is pretty well behaved. I think that all its rings are within Roche limit. So let's get to Quaoar. Quaoar is over here. It's the second moon on the left in the bottom. It has one known moon, Waywight. What's interesting about this is a chart that shows the largest known, I think, objects that are in the trans-Neptunian area, and they're all compared against the moon and the Earth down below. What's interesting about this is you look at each one of those small objects, and almost all of them have moons, which is kind of interesting, I think. But not only that, but you look at Haumea and also Quaoar here, both of those now have known rings. So this shows you a little bit about where Quaoar is located in the Kuiper Belt. Sun is located here in the center, obviously, followed by Jupiter, Saturn, Uranus, and Neptune. And Quaoar is basically in an orbit that's not only beyond Neptune, but pretty much beyond Pluto also. This one gives a lot of data on Quaoar itself. I won't go into the detail on this, but we'll mention that this one definitely looks to be a rubble pile because of very low density. Estimated density is somewhere between 1.68 to 2.2 grams per cubic centimeter. By the way, the human body is about 1. We're basically a lot of water, so we're right around about the density of water. So Quaoar is something like maybe about 2 times as dense as a human body. Quaoar, by the way, is the largest object discovered in the solar system since Pluto at the time that it was discovered. And this is a picture that shows Quaoar with its moon Waywight. Let's see what I want to do here. Well, one thing that I think is interesting here is that the moon Waywight has a radius of only about 53 miles. So it gives you an idea how small the moon is. Now, this is an interesting plot right here. This is the plot that was made that enabled the scientists to actually discover that Quaoar had two rings. Like I said, about a month earlier, they got a, a plot similar to this, but they only had a good indication that it had one ring. But this now shows that it definitely has two. What this is it shows a light curve. This is a light curve. On the left-hand side, the vertical scale is the magnitude of the light, normalized magnitude. On the horizontal scale, is the time. So what you do is you train your telescope on a star that you know is going to be occulted by the object that you want to investigate. So as time goes on, you would expect that the object that is going to do the occultation would be the one that gives you a clear indication as in the middle here that it exists because it blocks the light. However, before you get to that point, you can see that there are two other places where the light curve dips. And that's a clear indication that there's something else in the vicinity that's blocking the light. And what really does the trick, showing that it's a ring, is because the same pattern exists on the right-hand side. Well, almost the same pattern. What happened here in this case is that if you count from the left, you have one light dip, 2, 3, which is Quaoar, 4 and 5. Well, 2 and 4, 1, 2, 3, and 4. So you have 2 and 4 are very similar, which is the ring, but you have a completely different asymmetrical result looking at the light curve at 1 and 5. And that's a clear indication that the ring is not uniform in thickness and must be clumpy. So this is a little bit of information relative to what they have discovered with respect to the rings. One thing that is interesting to note on here is the resonances. It turns out that when they did the calculations for the location of the rings, well, first of all, there are two rings, obviously. The first one that I show here is the inner ring. That's Q2R. The second one is Q1R. Well, the reason why they're not ordered or numbered in order is because of the fact that Q1R, the outer ring, was discovered before Q2R, so they got reversed. But anyway, what's interesting about Q2R is that it is in a 7 to 5 spin orbit resonance with Quaoar. So there's a resonance effect already with that ring. Well, looking at the second ring, which is Q1R, they found the same type of thing, but different resonances. Turns out that Q1R ring is bounded by two different resonances, a 6 to 1 and a 3 to 1. So that's a very good clue that maybe those rings may have been around for quite a while. But on the other hand, it turns out that the resonance may have played a part in the actual location of where those rings are. So this is a depiction that shows exactly what we know about the Quaoar and its rings along with its moon. It's kind of interesting, but you can see if you look over here on this ring that is double, that there are two resonances that are keeping that ring in place. And this is a artist depiction of Quaoar with its two rings compared to two other objects, Haumea and Tiriclo. Tiriclo, by the way, is the smallest object known that has a ring. But you can see what's interesting about I'm sorry, get back over here. Q1R is way out there. And in fact, if I go back here, whoops, whoop, look at where the Roche limit is. Those rings, both of them are outside the Roche limit. And you look at Q1R in particular, it's pretty far out. And nobody knows why. The question is why didn't a moon coalesce there instead of having a ring form? And that's a major mystery. And hopefully, with further investigation, we'll come up with an answer. And that may lie in further spacecraft exploration. I'll show you that in a little bit. This is an illustration over here. This is the same type of plot as what I had shown you before. Different planetary bodies or solar system bodies that have rings with a common radius. And if you look over here on the extreme right, you can see where Q1R is with respect to Quaoar. It's way out there. So it's way beyond the Roche limit. And the key to understanding, I think, the formation of the planets may lie with the answer for answering this mystery. So that gets us into resonances. Now, there are three different resonances that I'm aware of that astronomers track within the solar system and elsewhere. The first one is what I call the orbit-orbit resonance. It's basically a resonance between two bodies that have to do with their orbital periods. So that's a very simple one to calculate. It's a very fundamental property of a planet to come up with its orbital period. So it's easy to come up with. The next one is a spin-orbit resonance. At least that's what I call it. It's a resonance between the rotational period of a body and an orbital period. So you not only have an orbital period involved, you also have the rotational period involved. Then the last one is a spin resonance, and that occurs when the rotational periods of two bodies have simple numerical relationships. So there are three different ones. By far, the most common one is the orbit-orbit resonance, followed by the spin-orbit, and then following with the spin-spin. So let's go into that. I'm going to show you the resonances that exist that we know about today within the solar system, starting with the inner solar system. And this is basically all the resonances that I am aware of within the solar system or inner solar system. These are two different resonances. The ones on top are the orbit-orbit resonances, and the ones on the bottom are the spin-orbit resonances. There's really not much to point out. I will say, let's see, one thing that I found out in this investigation is that Venus has a quasi-satellite, a satellite that revolves not only around the sun, but also around Venus, but it's only temporary. Well, guess what? The Earth does too. It has, in fact, 7 quasi-satellites that we know of right now. And being in the same orbit, basically those resonances are what are called one-to-one. Then besides those, there's the spin-orbit resonances. And one thing I'll point out here is that all the moons of all the planets that are known today that are spherical in shape, basically, are known to be in one-to-one spin orbit resonances with their primary planet. What that means is that you have the moon always facing the planet. And that's very true, especially with the Earth. As you know, when I was a kid, I thought that was very special. I thought isn't that a great coincidence that the Earth is set up with a moon that always faces it? Turns out that it's not special. It turns out that all the moons that we know of that are big enough have that same relationship. And we go on to Jupiter and Kirkwood. Okay, when I said 1867, it was Kirkwood who came up with what are called the Kirkwood gaps. There was enough information that had been gathered on the asteroids in 1867 that Daniel Kirkwood was able to come up with what are now known as Kirkwood gaps. He could see that based on the orbital elements of the known asteroids, that there were gaps within the main asteroid belt. And this is a neat plot here. This is actual data. But this is actual data that has been normalized to bring out the features of the Kirkwood gaps. And it's a real neat plot. I like it because it is real data, but it's been normalized. But it really brings out where the Kirkwood gaps exist. What you're looking at is the solar system out to Jupiter. In the middle would be the sun, followed by Mercury, Venus, Earth, Mars, and Jupiter. You can easily see the Trojan satellites of Jupiter at the L5 and L4 libration points. You can also see the Kirkwood gaps in the main belt here also. So I like that. That's when you can see how those Kirkwood gaps actually exist. This is a plot. It shows on the vertical scale the number of asteroids versus on the horizontal scale, the distance they are from the sun. And this plot, again, shows you the Kirkwood gaps pretty easily. You can see where, you have places where you got a lot of asteroids. You have other places that really don't have hardly any. And those places that don't have hardly any are Kirkwood gaps. The thing of it is, what's interesting about this is those Kirkwood gaps are not random. They are caused by resonances with Jupiter. And there are two types. There are some resonances that actually build up, allow asteroids to build up. You have other resonances that clear out the asteroids. So the asteroids the resonances that clear out the asteroids produce the Kirkwood gaps. But when I was in college, nobody told me that the places in the main belt that did not have gaps also were a result of resonances. And I thought that was, I think that's very important to bring out. It's sort of like the case where you're missing the forest because of the trees. You're looking at the gaps, but you're missing the main show. This is another plot that brings out a little bit more. And what's more interesting here is that, okay, let me just show you. You can see, well, here again, this is a plot that shows the number of asteroids versus their distance from the sun. Okay, so every place where there's a resonance, I have a little line here that shows where those resonances are. So you have a 4-to-1 resonance that basically defines the inner part of the asteroid belt. You have one at 3-to-1, which is the Kirkwood gap. You have one at 8-to-3, which is Kirkwood gap. You have one at 5-to-2. You have one at 7-to-3. You have one at 9-to-4, and then you have 2-to-1, which defines the outside of the Kirkwood. I'm sorry, outside of the main asteroid belt. What's interesting here is look at where the arrows is that arrows are that I have put on this plot. Those arrows all exist within the places where there are no Kirkwood gaps, but those are places where you have what I call three body resonances. The blue arrows are asteroids in resonance with Jupiter and Saturn. When I was in college, nobody told me anything about Saturn having anything to do with the asteroid belt. But lo and behold, those blue arrows are places where you have a three body resonance between the asteroids, Jupiter, and Saturn. I thought that was very interesting. Another thing, too, is this green arrow. That green arrow is another three body resonance, but it has nothing to do with Saturn. It has to do with the Earth. I thought that was very interesting. I never knew that the Earth had anything to do with the gaps in the asteroid belt. Another thing here, too, let's see, there was something else I wanted to bring out. Let's see if I can remember. I think that's going to probably, oh, I know what I want to do. What's interesting about this, too, is look at the 3-to-1 resonance where the Earth is involved. That gap is not a real gap. It has asteroids in there. Those asteroids are living very happily in the Elchert asteroid area. That's where the Elchert asteroids live. Another thing, too, you look at the 9-to-4. The Eos asteroids live there, too. So the thing of it is would you say that the 3-to-1 and the 9-to-4 resonances where you have the gaps, are those destructive resonances or constructive resonances? It looks like for some asteroids, they're constructive, for others, they're destructive. So it's kind of interesting. Okay, here's another satellite. This is Lucy. This is a satellite. This is a spacecraft that is going to be launched next month. It is a big one. It has two large antennas here for radioing back data back to Earth. Its destination is 2 main belt asteroids plus 8 Trojan asteroids. It's going to be visiting a lot of asteroids, and hopefully it's going to be able to bring, send back data that's going to enlighten us on what, basically give us more information about the asteroids and allow us to figure out things a little bit better than what we currently know. It's a 12-year mission, takes off in November, and will end its, what's that? Oh, it took off already. You're right. I'm sorry. No, that's right. I remember. Yeah, it was launched a couple of years ago. It's going to have a flyby. Okay, so mark your calendars. Thanks very much, Gary. Mark your calendars. Lucy's going to make its first encounter. It's going to have a flyby on November the 1st. That's less than a month away. Okay. Thanks very much, Gary. Okay, so these are the asteroids that it's going to encounter. Now look at this plot here. There's some very interesting things here. First of all, note the rotation of the asteroids it's going to encounter. They're not all rotating in the same direction, which more or less is what you might expect if they're produced by some kind of a, impact or something. The other thing, too, is that what I show here is Patroclus and Menomonaeus. Those are twin asteroids. They're in orbit around each other, and they both are looking at each other as they're in orbit. So that's going to be a very important observation that's going to be made by Lucy coming up. I think it's going to be March of of March the 2nd of 2033, about almost 9.5 years, or about 9.5 years from now. But that's going to be a very interesting mission. It's going to be finding out a lot of different things about different asteroids on that. Okay, this I think is amazing. We're talking about OSIRIS-REx having come back with its payload, landing in Utah this last Sunday. A lot of people think that that's the end of the mission. That's not it. OSIRIS-REx is still in space. What came back was the capsule. OSIRIS-REx is going on its extended mission, and instead of being called OSIRIS-REx, it's called OSIRIS-APEX, which stands for Apophis Explorer. Well, Apophis is an asteroid which is going to go to, and it's going to make a close observation of that asteroid. What's amazing about this is where it's going. Apophis is going to go to Earth, come to Earth, and it's going to make a close encounter April the 13th of 2029. It's going to be so close to Earth that people in Europe can go outside at night and see the asteroid come right by. And right behind it, 50,000 kilometers, will be OSIRIS-APEX. So mark your calendars again. April the 13th, 2029, we're going to have a very close encounter with Apophis with OSIRIS-APEX trailing right behind it. The thing that you have to watch out for is April the 13th is also a Friday. So Friday the 13th, if you have the guts, fly on over to Europe and get, view the show. But that ought to be fantastic. Yes. What's that, Joe? Well, I'm hoping too. Here's another case where we're pretty optimistic. Here you have the U.S. Postal Service saying we're going to issue a stamp before the event happens. Well, here I'm announcing an event before it happens also, but the event is going to happen on April the 13th. So cross your fingers and hope that everything works okay. Now, this is a neat plot here. It actually shows the Earth's attraction on Apophis during the encounter. On the vertical scale, you have the force, the gravitational attraction by the Earth on that asteroid. On the vertical scale, you have the time. So during the time, it looks like to me about plus or minus 25, what is that, 25 hours. Apophis is going to be well within the Earth's gravitational field, and it's going to bend its trajectory. In fact, the force is going to be the gravitational force is going to increase up to 45 times what I guess it's going to normally be. So it's going to be significantly changed. So what I'm going to show you here is that, let's see if I have it on here. Yeah, what's going to happen is its orbit will be changed from an Aten class asteroid to an Apollo class asteroid. So not only is its orbit going to be changed, it's going to be significantly changed to make it a different class of asteroid. That's the first time I think that we've ever encountered anything like that. Psyche. I checked this morning on Psyche. Psyche is a spacecraft that has not yet been launched. The launch is going to be coming up on October the 12th, at least what I checked out this morning. That's less than two weeks away. Its destination is, believe it or not, an asteroid called Psyche. Okay, Psyche is a different kind of asteroid. I've been talking about rubble piles. Psyche is not a rubble pile. Psyche is metallic. It has a very high density. It's full of metals. In fact, it's so full of metals that they estimate that it's worth about 10,000 quadrillion dollars. Now, the thing about it is that when NASA first announced that it was going to be going to Psyche, Ron, our 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 in-house resident here on the PVA board, immediately called up NASA and volunteered to go on board. Is that true, Ron? Oh, but anyway, think about it. 10,000 quadrillion dollars. That is equivalent to something like about 91,000 times the world's economy. So that's a very valuable asteroid. Yes. Okay. How do they know that? One of the things that the astronomers do is they'll take light curves of various asteroids. From the light curves, they can deduce what it might be made of, basically based on the meteorites. Okay, so you have chondrite meteorites made of stone and things of that type. You also have metallic meteorites that are made of iron and nickel. And based on the spectrum of those types of objects, comparing those to a light curve that you might get from an asteroid like Psyche, you can deduce what kind of material it's made of. But they know, but the real question is, how do they know the density of Psyche? And I think that the only way that they have come up with the number that I show on here is based, instead of making a measurement, they have based their estimate. It's an estimate based on the fact that it's made of metals. So backwards way of doing it. But anyway, that's going to be another one. It's coming, its launch is coming up on October the 12th. So mark your calendars for that. It's going to be going to Psyche and ending its mission on May of 2031. Oh, that's a good question. No, I don't. It's not a lander, so I don't think that it's going to happen. Okay, so going on with the resonances here with Jupiter. Here again, I have two different kinds. We have the orbit-orbit resonances on the top and the spin-orbit resonances on the bottom. The spin-orbit resonances on the bottom are just the basic tidal capture of the moons. Where you have one moon, you have each moon basically looking at the same, in the same direction of the, yeah, just like our moon. Yeah, same thing. Yeah. One thing I'll point out here, you look up here on the orbit-orbit resonances, we have Io, Europa, and Ganymede. You have three different moons, and they're all in resonance. They're all in sequence. So it's a three-body resonance, 421. And the 421 resonance is an interesting one. I'll show you on the next chart. This is not the scale, but it basically gives you the same type of information. Oh, I don't know if I'm going to be able to stop this. Is there a way to, oh, maybe I can just do this. Let's see. Yeah, I can do it. Whoops, it doesn't do it. Let's see, hang on here. I'm going to go back to Jupiter. Is there a way that I can press on this without changing the page? Just, yeah, what I want to do is just to press on here and stop the animation. That's okay. But anyway, that's okay. I'll just speak it. What happens is, because of this resonance, those three moons, Ganymede, Europa, and Io, never appear all together on the same side of the planet. Their apexes, or what would you call it? It's not aphelion, but apogee, whatever you might call it. The apogees on this are always set up so that two of the moons will be on one side, the other one will be by itself. So I thought that was kind of interesting. Okay, talking about Jupiter, we got a spacecraft again that's going to be flying to Jupiter. It has already launched. This is JUICE. The JUICE is a European Space Agency vehicle. It was launched in April. It's going to have a Venus flyby in August of 2025, and then it's going to go into orbit around Jupiter in 2031, and then it's going to be going into orbit around Ganymede in December of 2034. So we got another spacecraft that's going to be going into orbit around a moon of Jupiter. There's also another spacecraft called the Europa Clipper. It's going to be going into orbit around Europa, and that'll be launching next year in October. So we're going on to Saturn's resonances, and same type of thing. We've got a bunch of resonances that are shown here. Saturn is a planet that's known for its rings, and it obviously has a lot of interaction between its moons and its rings. It's shown on here pretty well. There's also resonances between the moons and well, just between the moons themselves there. It's kind of interesting to go through this. I won't spend a lot of time. We'll just point out one thing here. There is what I think might be a four-body resonance. I've never seen it called it that way, but it looks to me as there may be a resonance that is between Mimas, Anthe, Janus, and Epimetheus. I'm going to have to do a little bit more research on that, but I think that might be the only four-body resonance I've ever found in the solar system here. This is a ring, rings of Saturn laid out. It goes from the D ring on the left to the F ring on the right. And those rings have a lot of different features in there. A lot of those are caused by the moons, and a lot of those are due to resonances, especially the gaps. For example, if you look over here on the right, on the right-hand side, you got the Huygens gap. That's caused by Mimas. And then over on the right hand of that, you have two gaps. You got the Encke gap and the Keeler gap. And those are caused by the moons Pan and Daphnis. But here again, a lot of the ring features are due to resonances, and it'd probably take a whole lecture just to go through and give details on that. But I think you get the idea that there's a lot of features that are in the ring system of Saturn that are basically due to resonances between the rings and the moons. And again, we have these are tidally locked moons of Saturn, where they all face Saturn all the time. There's one hemisphere that always faces Saturn. The other hemisphere is facing away from Saturn. Then we go to Uranus, and we've got a bunch of resonances here. I'm not going to speak much on these. Pretty much the same type of thing. Then go on to Neptune. Neptune is a little bit more interesting. Neptune has a three-body resonance between Galatea, Larissa, and it's what's interesting about Neptune is it has ring arcs. So those ring arcs are basically interacting with gravitational effects from Galatea and Larissa. And that's kind of a neat thing. Another thing, too, that I'll point out is uh, we have one resonance here. It's between Neptune and one of its quasi satellites, and that's a 36-to-1 ratio. I have never seen anything quite that big in any of the other planets in the solar system. This is the highest ratio, you might say, for resonance, and I thought that was amazing that you would have 36 orbits of one body affecting another body that makes one orbit in that same time. So that was interesting. One thing that I found that was kind of strange, I don't have a real good explanation for, is this chart right here. On the vertical scale, I have the inclination of these bodies. These are all trans-Neptunian objects. These go from around about the orbit of Pluto on out. Those objects they have been given different names. For example, objects that have I guess it would be a 3-to-2 resonance with Neptune are called Plutinos. They're called Plutinos because Pluto has a 3-to-2 resonance with Neptune. Well, guess what they call the objects that have a 2-to-1 resonance with Neptune? Those are called Tutinos. Okay, so what do you call the objects that are in between the Plutinos and the Tutinos? Well, they're called the cubanos. And I think I don't really know why they're called the cubanos, but what I find interesting about those is that they're all pretty much right at the 7-to-4 resonance. And yet they're defined as objects that do not have any resonance with Neptune. And I find that very strange because when you look at where they are located, they're all aligned with the 7-to-4 resonance. I don't know why that is. I just find that kind of interesting. I wish I had an answer, but I don't. This is another plot of the same type. This is showing the number of objects on the vertical scale versus distance from the sun. This is showing those objects in the Kuiper belt spread out. And you can see where the 3-to-2 Plutinos are and the 2-to-1 Tutinos are, and the cubanos are in between. And lo and behold, you got something here right in the middle that really overwhelms the whole plot here. They're called the kernel. I don't know why they're called the kernel, but they're right there in the cubanos. And why this is not called a 7-to-4 resonance, I really don't know, because that's where the 7-to-4 resonance occurs. I actually calculated it, and I was really surprised. So that's a mystery that maybe some of you could solve. I don't know. So I'm going to wrap this up with my last chart here, and I'm going to point out something on this one. I think that is going to basically be the highlight of the presentation, maybe. Let's see if I have another one here. I guess I actually have 2 points on this one. The first point is if you look at the first star up there on the top, I have a star there for a resonance between Styx, Nix, and Hydra. That is a 33 to 22 to 18 three-body resonance between the satellites or the moons of Pluto. Now, I thought that was kind of interesting. And I thought that, if you're ever on Jeopardy and you're asked the question, what is the significance of Styx, Nix, and Hydra? You now know the answer. But anyway, I thought that was kind of neat. It's kind of a strange resonance, with numbers that high. You're usually dealing with resonances like 5 to 2 or 7 to 4 or whatever. This is 33 to 22 to 18. But what I really want to point out on this one is maybe a key to the mystery that I started out with respect to quasar. If you look on here, I show that there is a 3-to-1 spin orbit resonance for not only quasar in the Q2 ring, but also, for the Q1 ring, I should say, but there's also a 3-to-1 spin orbit resonance with the Cheriklo in its ring and Haumea in its ring. That may be some kind of a clue as to what is going on with quasar. I really don't know, but I don't know, and it might be just a coincidence, but that's what I'm going to leave you with. I'm going to leave it to you to solve the rest of the problem. If there's any questions, I'm here to answer. Yeah, man. Yeah.
So a few slides back, you showed that Saturn has just a ton of moons.
Yes.
That are in a 1-to-1 spin orbit resonance.
Yes.
They're tidally locked.
Yes.
Saturn. Is that something that can be predicted theoretically, or does it have to be observed?
I think that resonances, one element that is really required for a resonance to occur is time. Over millions of years, you're going to have resonances that are built up. I would say that if you have enough information about two objects, let's say a planet and its moon, you can probably propagate in the future, to the future, whether there may be a resonance that may be built up over time. I really don't know. I would assume that could be the case, and I don't know if that's ever been done. I do know that, and I was talking to Ron about this earlier, there are instances that are known to exist where you have coincidences that look like resonances, but they really aren't. And the key to that is computer simulations. If you have what you think might be a resonance and you put in all your data that you know about those, and you propagate their orbits over time, and if what you're looking for, if it's a ratio of periods or something that you're looking for, and they don't change over time, that's a true resonance. If that parameter actually does change with time, it's probably just a coincidence. And like I was telling Ron, there's a really good coincidence. If you look at Venus and the Earth, you look at their two orbits, the orbital periods, it looks very close that there's an 8 to 3 resonance between the Earth and Venus. And you would swear, by just doing your own calculation that, yeah, there is a true resonance here. But there isn't. When you put in your numbers in the computer and you run that over time, that relationship changes. But yeah, it's a tricky thing sometimes when you do. If you don't have a supercomputer and you come across something that looks like a real good resonance, you could be tricked. Mother Nature is nasty sometimes, you just don't know. But I think that the key a lot of times has to do with time. You can predict, I think, things in advance. But a lot of times, you have to probably run. In fact, I've heard them running their simulations for something on the order of millions of years. This is not something that they do just for a few thousand years. It's usually on the order of 1 million or more years. That's where you need a supercomputer.
I was curious. There's one that tripped somebody up. The science fiction author Larry Niven back in the 60s he published a story called The Coldest Place that had people crashing on the backside of Mercury, which was at that time thought to be tidally locked to the sun. And he thought the dark side of Mercury would be one of the coldest places in the solar system, because there's nothing particularly close to it to be bouncing back any reflected sunlight. And within a year or two of that story being published, I'm not sure if it was one of the Mariner probes or if it was bouncing radar off of Mercury, but they found out it was in a 3-2 spin orbit. So it actually does turn, and it's not tidally locked to the sun. And that story had been popular. He was like, oh, yeah.
Well, talk about bad timing, huh? That's the thing. Talking about that particular resonance there, I didn't point it out, but yeah, that is a true resonance, obviously, and I think that may have been discovered by one of two methods. Like you said, it might have been the Arecibo radio telescope that may have done the observations, or it may have been Mariner 5. I think that Mariner 5 or 10. No, I think it was Mariner 10. Mariner 10 went by there, I think right around about 1974, 75. But yeah, that's bad timing. Interesting.
On the explanation of the outer rings, when the object is coming close to the Roche limit and it explodes, is it possible that the explosion would force it out far enough and then be captured by gravity to form the ring? Or not?
Now, when you say force it out, when
just the force of the explosion itself.
Well, see, I look upon it as not so much an explosion, but a disintegration. I don't look, unless it has internal gas pressure.
Yeah.
I would imagine that most of these objects that are broken up by entering, going past the Roche limit are probably just disintegrated. I don't think that there's much of any explosion outwards. But if there was, that's an interesting thing. I would imagine that those particles that would have their trajectories going inside the Roche limit will create a ring. For those objects outside the Roche limit, they may also eventually form the ring if they spiral, their orbit spirals in. And see, like the moon, our moon is spiraling out. Mars's moon, Phobos, is spiraling in. Why is that? The key is angular momentum. The moon is beyond the geosynchronous orbit, so it's spiraling out. Phobos is inside of its geosynchronous, well, it's not geosynchronous, Mars synchronous orbit, so it's spiraling in. So I think maybe part of the answer has to do with whether those particles, where they're located. Are they outside the geosynchronous orbit or inside? That's a good question. Yeah.
So did you buy those stamps?
Yes, I did. In fact, let me tell you what happened. I went to San Dimas and I asked the guy there, do you have the Osiris Rex stamps? He had no idea what I was talking about. So he said, do you have a picture of him? I said, well, I don't have my phone with me. So I went back the next day with my phone and I asked him the same question. Do you have these stamps? He said, no, I've never seen them. So I went to the Glendora post office and they had them.
Okay.
But if you're interested, I'd recommend you go on there, but go to the right post office. Don't go to San Dimas. Okay, that sounds good. Yeah. Sounds good. Okay, well, thanks everybody for attending. I appreciate it. Okay. Now, I'll have you